So it is my great pleasure to introduce Dr. Little, who received his BA and doctorate degrees in material science from the University of Oxford, and postdoctoral. His appointment in 1990, he arrived at Bell Laboratories, spent the next 11 years there. His primary efforts are directed toward research, development, and eventual commercialization of a novel electron beam lithography technology. He is currently scientific director of the Microsystems and Nanotechnology Division at NIST. His division works in a variety of areas ranging from quantum nanophotonics to biology. His personal research focus is on nanofabrication and self-assembly for nanomanufacturing. He's published over 275 papers in areas ranging from electron beam lithography to DNA-controlled nanoparticle assembly and holds 19 US patents. He is a fellow of the APS and the Washington Academy of Sciences and a member of the AVS and MRS. He has served on numerous advisory and program evaluation committees, including those for NSF, DOE, and the Semiconductor Research Corporation. It is my great pleasure, and I ask that you join in welcoming Dr. Little.
Thank you, everyone, for, I guess, staying home on this rather damp afternoon and listening to this talk. So what I wanted to do was give a little bit of background about my primary research focus area, which is on DNA nanostructures, a particular way of fabricating nanostructures. And for this audience in particular, I'll try and explain how it might be useful for various applications in healthcare, and if time permits, maybe a few comments on how it might be useful in applications beyond that space. But before I get going, I'd really like to sort of set the scene or set the scale and explain sort of where DNA nanostructures fit in sort of technology terms relative to other types of nanofabrication and natural structures. So on this slide here, you can see a view of some man-made things and some biological things. In the upper left, there's a picture of a red blood cell. It's about 7 microns across and contains a lot of detailed structure in the form of various biomolecules, the most important one of which, of course, is hemoglobin, which you can see at the bottom right. And that is an object that's only about 5 nanometers across. In the middle of the screen, you can see a couple of views of a cross-section of a modern integrated circuit. Again, the image on the left-hand side, the integrated circuit image, is at the same scale as the red blood cell. So you can see that there's an awful lot of detailed structure packed into an equivalent kind of space. Next to that is a close-up of what lies at the bottom of that stack of structures that you can see. And those are a couple of leading-edge transistor structures. So you can see sort of 3 elements piled on top of each other for each of those transistors. And the individual feature size in those is around 5 nanometers or so, roughly the same length scale as the hemoglobin molecule you can see. And we're able to control those features to within just a couple of atomic dimensions. So there are a couple of takeaways here. One is that we're now through what we call top-down nanofabrication, where we impose structure on a material, able to create things that are on the scale of some of the smallest structures in biology. And the second message is that, with that in place, we're now able, in principle at least, to interface with biological structures at the very smallest length scales. So what I want to do next is talk about how we might have a technology that sort of marries those two together. Can we, in fact, find a way to build molecular structures as opposed to just sort of deriving them from biological systems? So I wanted to give you an example of why we care about this sort of thing. And this seemed like a very timely example of what nanotechnology can do for you. So on the screen, you can see a representation of a drug delivery, or in this case, vaccine delivery vehicle. The red strand in the middle is supposed to represent mRNA. That's the thing in some of the COVID vaccines that actually goes into your cells and encourages them to produce the viral protein that then stimulates the immune response. But that piece of RNA can't do its job without all the surrounding material. That surrounding material is in fact a lipid vesicle, and that is the thing that allows that piece of RNA to travel around your body, make its way into a cell, and do its thing. And this next slide shows this in a little bit more detail. One of the things that had to happen, and it's taken many, many years to achieve this, is to actually chemically build the necessary combination of lipids. There are a couple there, along with some cholesterol, what's called a pegylated lipid, that's polyethylene glycol, that enables the construct to avoid the immune system to a large extent. And again, through this immense effort in synthetic chemistry to build lipids that can actually transport the RNA into a cell without destroying the natural cell membrane, that will degrade appropriately, release the RNA in the right spot, and again allow it to be used for the synthesis of the viral protein and promote the immune response in that way. So this is a system that already looks relatively modular, but again, I want to emphasize the degree of sort of chemical engineering, chemistry that had to happen in order to configure it to deliver its payload and be an effective vaccine agent.
Thank you so much, Alex. I wanted to just say it's amazing to see the effort that's gone into this, the understanding that we have now around these structures, certainly from the chemical engineering discipline, but all the other technologies and disciplines that are coming into play. And certainly leading to therapeutics. That's what we want to hear in healthcare, the application of all that knowledge. So thank you for that. I'd love to, at this time, introduce Paul Sheedy. Paul is an entrepreneur and strategy expert, co-founder of both the World Nano Foundation and World Science Aid. He has a degree in chartered mechanical engineering and began his career at the Ford Motor Company before starting his own consultancy 30 years ago, which has grown into an international group specializing in strategy implementation for highly disruptive startups through to global brands. The propriety approach has been used to enhance the effectiveness of global conglomerates, generating billions in forward revenues and profits. Paul believes that all strategy comes down to two questions: what business are you in, and how are you going to win? These questions are simple but not easy. Paul and his colleagues have developed analytical tools to assess the likely success of disruptive technologies coming to global markets, and similar mechanisms to pick strategic winners in developed yet changing markets. It is my great pleasure, and I ask you to please join me in welcoming Mr. Paul Sheedy. Paul?
Lucia and Christoph, thank you very much for the invitation. And Alex, thanks for setting the bar so high to follow you on with my presentation. That happens a lot in our line of work. We meet a lot of exceptionally talented scientists like Alex and stuff. And I want to talk a little bit today about the foundation, its function, and what that means for the future of healthcare. So the foundation, the World Nano Foundation, was founded about 5 years ago. The co-founder is Paul Stannard. He's a media guy. I'm an engineer. They start to make sure that we find the nanotechnologies that will change the world for the better. There's lots of great nanotechnology investment going on. It tends to be a bit siloed within countries. So we wanted to internationalize it and bring better cooperation between people in different parts of the world to help nanotechnology progress. And we have a nano magazine that I would encourage you to go and seek out, which covers kind of the best stories of the week in terms of nanotechnology. Okay, so Alex has done a little bit of this. So nanotechnology is quite an interesting statement because it's just a measurement and stuff. So, Alex has said, the kind of scales that we're dealing with. So I kind of, just to follow on that is like Alex showed you, the red blood cell is kind of 7,000 nanometers. It's also interesting, a strand of DNA, as he showed, is 2.5 nanometers. But I kind of looked up today, just for the purpose of this, that the coronavirus itself, the little demon that we're dealing with, is all of 100 nanometers wide. And the spikes that you hear so much about in the virus are about 10 nanometers long. And the receptors, it will vary a little bit, but they're about 20 nanometers. And then that's kind of in the biological kind of current phase. But also I was recently looking at an Apple advert where their latest chip has improved their technology from 7 nanometers tech to 5 nanometers tech. And that's allowing them a 60% or 40% increase in power to 1.7 trillion operations per second. So how that backs up a little bit of what Alex was saying, that the power of nanotechnologies at that level is quite impressive. So when you start to engineer at those particular levels, the solutions that emerge are truly amazing, and the possibilities that emerge that are amazing, which I think Alex has shown one insight into, but there's plenty of others in terms of how it works through the nanotechnology world. So how we experience and how people in healthcare will experience the effect of nanotechnology is when it percolates itself up into the element of being a solution, a treatment in healthcare, something that hasn't been treated before, a better way of treating something. So, but we rely upon the brilliance of people like Alex to have done all the work at the very basic level and to build platforms that are like the breadboard and that Alex showed you in his presentation, that allows us to build on top of those platforms into engineering solutions. And one of the things that we find is it's quite incredible once a nanotechnology platform is being developed, that sometimes it's the uses of it and the solutions that can be engineered from it can be in completely different industry. They can be in material science and they can be in healthcare because of the fundamental work that they are at the basic and the kind of fundamental piece of engineering how things work. So if you think of things like the kind of platforms like Alex's platform, CRISPR, the amazing work that DeepMinds have done with their AI system and AlphaFolds, which predicts how proteins are likely to the structures of proteins from how their sequencing. It's just, and then you add that to the decoding of the genome, and what you're finding, and we see other technologies that allow, which Alex again mentioned, the delivery of these new solutions into the actual cell without damaging or killing the cell to do it. So if you put those things together, and it's only some of the elements that are platforms that are being developed, we're at an incredible juncture in time where these incredible, almost limitless solutions can be built upon the platforms that have been developed by the world's excellent nanotechnologists.